Assalamu alaikum wa rahmatullahi wa barakatuh. So, in the last lecture, we discussed about the integrators and differentiator. Today, we will see some special type of circuit which is used to filter out the unwanted signals. Okay, suppose if you consider a signal, consider a signal, uh, consider a signal. Let's say a voltage signal V of t. Okay, now this signal can be, suppose it like this. Okay, this is a signal like this. This signal contains many frequencies. That means that this signal can be, your signal V of t can be written as the combination of many signals. For example, this contains a signal in okay, this contains many frequencies. For example, it contains frequencies from 0 hertz to maybe 1 megahertz, for example. Okay, now this is the time axis. Okay, and this is V of t. Now, if you don't want all these frequencies, and if you want to remove some set of frequencies, suppose you need only, or you are interested only in suppose you need only some set of frequencies. For example, you need the frequencies from 0 to 1000 hertz. Then what you have to do, you have the signal V of t which contains the frequencies from 0 hertz to 1 megahertz. That means that it contains all the frequencies in between the range 0 to 1 megahertz. This signal is a combination of many signals in between the range 0 to 1 megahertz. You will use a special circuit. And if you pass your input signal through this, you will get an output signal. Okay, you will get some V out of t which contains the signals only from, you can say from, for example, 0 to 1000 hertz. So what is this special circuit? This special circuit is nothing but a filter. That means you are filtering out all other signals. So this filter will filter out, this filter will allow the frequencies from 0 hertz to 1000 hertz, and it will not allow the frequencies above 1000 hertz. Okay, so whatever the frequencies which are between 0 hertz and 1000 hertz, it will be allowing by this filter. This filter is a special filter which is designed for this particular range of frequencies. So you can design another kind of filter which are suitable for another frequencies. So it will depend upon the design of the filter, and it will not allow this, you see, it will not allow the frequencies above 1000 hertz. Basically, this filter is a low pass filter. I will come to this terminologies later. So what is filter actually? So filters, so today's topic is filters. So filters are the circuit that passes a certain range of frequencies, okay, and it will not allow, that means that it attenuates or rejects means it will not allow. Okay, it rejects all other frequencies. Okay, so whatever we have seen now, that means the filter which allow the frequencies from in a lower range. You see it is a lower range, you can see this is a lower range, 0 to 1000 hertz, it is a lower range, and whatever which is not between 0 to 1000 hertz, that is nothing but above 1000 hertz, it is not allowing, and this filter is a low pass filter. Okay, so we can classify the filters into 3 types, not 3 types, actually 4 types. It is a low pass filter, then high pass filter, then is the band pass filter, and it is a band reject filter. Another one is band reject filter. Okay, so we will come to all these things later. Now you see, what is low pass filter? It will allow the range of frequencies, it will allow all frequencies below some particular cutoff, that means below a cutoff frequency. In our previous example, the cutoff frequency is 1000 hertz. That means it will allow all the frequencies below 1000 hertz, and it will not allow the frequencies above 1000 hertz. And what is high pass filter? It will allow all frequencies above a cutoff frequency, okay, it's frequency, cutoff frequency. Okay, and what is band pass filter? It will allow all frequencies between lower and upper cutoff frequency. That means between some particular range it will allow. For example, it allows frequencies between some 10 kilohertz and 20 kilohertz. It is a band pass filter. That means it is allowing only the frequencies between a particular range. And what is band reject? Band reject is just opposite of band pass. Okay, it will block or block the frequencies between the lower and upper cutoff frequencies. Okay, frequencies. So between, it will block, okay, it will block the frequencies between lower and upper cutoff. So I will draw the diagram. So I will draw the diagram, the frequency response of these filters. Okay, so the frequency response of filters. Okay, filters. So first I will talk about the low pass filter. So if you take the low pass filter, the frequency response will be something like this. It will be like this. Okay, we have already seen this response when I told you about when I discussed the op-amp characteristics. So this is the gain. Okay, the same notions are valid here, and this is the cutoff frequency. So you see here, it is allow all the frequencies from 0 to Fc. So 0 hertz to Fc hertz it allows, and the gain, you see there is a gain here, and between this range actually you see after Fc the gain is very small. That means it is not allowing. Okay. So this is 0 dB, for example. 0 dB means what? Actually the number is, the gain is equal to 1, for example. Okay, so this is the low pass filter. So low pass filter I will call LPF. Okay, this is low pass filter. Then high pass filter I will call HPF. Band pass filter I will call BPF, and the band reject filter I will call BRF, okay, band reject filter. Now it is not allowing any frequencies above the FC heads. You see here there is a transition here basically. It is not so sharp. So this is a practical filter, I can say. This is a practical filter. But ideally we need the characteristics like this. You know, this is FC. This is the ideal characteristics. Your gain is 0 dB here. This is a low pass filter which is ideal. Okay, this is ideal. You see, up to FC the gain is 1 or 0 dB we can say, and after FC there is no gain. So this is actually the actual response of a good filter, or this is the ideal filter. This is the ideal filter, ideal low pass filter, and this is a, and the other one, the first one is the practical low pass filter. Okay, but we will not get these characteristics. It's very difficult to obtain these characteristics. Now what is so we will see more on the low pass filter characteristics now. Okay, so low pass filter characteristics, we will see this is the characteristics of a low pass filter practically. Okay, practically. Now the gain, I told you it is 0 dB, and for example this is your FC. Now for example this is 10 FC. For example this is 10 FC, 10 FC. Now at 10 FC the gain is, for example, you know, the gain at FC it is approximately 0 dB, and gain at 10 FC it become minus 20 dB. Okay, so the gain at FC I am saying it is 0 dB. Okay, and the gain at 10 FC, that means 10 times that frequency, it is minus 20 dB. Now the gain at for example this is 100 FC, the gain at 100 FC it is minus 40 dB. Okay, this is minus 40 dB, and this is going like this, and this is 1000 FC, the gain at 1000 FC, this is minus 60 dB. So all these are in dB. So its gain at 1000 FC it is minus 60 dB. So what is this characteristics? You can see a characteristics like this. So we can say that the gain is actually decreasing at a rate of minus 20 dB per decade. You see, if you consider this is FC, then this is 10 FC, that means that 10 times, that means that this frequency is 10 times FC, right? 10 times FC, that means it's 10 times. For example, this is 10 hertz, then this become 100 hertz, like this. Okay, and if this is if FC is 100 hertz, if FC is 100 hertz, then this become 1000 hertz. That means 10 times the frequency. This 10 times frequency we will call another name, which is known as decade frequency. Decade, it is decade frequency. Okay, so 10 FC is the decade of FC, then 100 FC is the decade of 10 FC, and 1000 FC, I will just write here 1000. Okay, 1000 FC is the decade of 100 FC. Okay, so what is happening here? The gain was 0 dB initially. After that it has become minus 20. First it was 0, minus 20, minus 40. That means in one decade, the gain reduces by 20 dB. That means suppose this gain is 0 dB, you are getting here as minus 20 dB. Then if this is minus 20 and this is nothing but minus 40, that means minus 20 dB is decreasing in 1 decade. That means that the slope, we can say the slope is minus 20 dB per decade. Okay, so this is the notation. So the slope is actually minus 20 dB per decade. So what I am saying is the slope is equal to minus 20 dB per decade. Okay, so the slope of this curve is minus 20 dB per decade. Okay, this is the slope of this curve. So there are some importance for this. So this is a low pass filter now, and this, if the slope is minus 20 dB per decade, I can actually realize this circuit by using this following in the following way. Suppose you have a V in, you know that this is R and this is your capacitor. I am talking about the low pass filter realization, and there is a capacitor here, and this is your V out. This is your V out. Okay, now what is this V out? You know that what is the capacitive reactance? It is 1 by j omega c. So what is V out? V out is equal to V in divided by, it's a voltage division, so it is R plus 1 by j omega c multiplied with 1 by j omega c. So what is this? This is V in divided by 1 plus, okay, 1 plus j omega RC, okay, 1 plus j omega RC. Am I correct? So because the other things will cancel, actually 1 plus j omega RC divided by, okay, I will write the whole step, 1 by omega c into 1 by j omega c. So you know that this will cancel, so this become V in divided by 1 plus j omega into RC. Now if you are using okay, that's it. Now you see here that if I am using the S domain calculation, if I am using this this capacitor as 1 by SC, you might have seen about this, then you will get this as, then you will get the V out as V out is equal to V in divided by 1 plus S, instead of j omega I am putting S, so 1 plus SRC. So this is your V in. Now you have studied about the poles and zeros in automatic control. So poles and zeros. What is poles? The poles is the root of the denominator in the transfer function. Denominator, the pole is the root of denominator in transfer function. And what is zeros? It is the root of numerator in transfer function. So here what is that? V out. V out is equal to V in divided by 1 plus S into R into C, or the transfer function is nothing but, transfer function is nothing but V out divided by V in is equal to 1 by 1 plus S into RC. Then the number of poles, actually what number of zeros, there is no terms of S, no terms of S here, so the number of zeros, so no zeros, no zeros, poles and zeros. I am talking about these zeros, not like our normal zero, standard zero. So it is, there are no zeros in the transfer function. And what about the poles? To find the poles, you will take this denominator 1 plus S into RC, you will equate to 0 to find the poles, So, S into RC is equal to minus 1. So, S is equal to minus 1 by RC, and you know that what is this? RC is the time constant and it is minus 1 by tau. So, you are getting actually how many poles? There is only the degree of S is 1. So, degree of S is 1. So, only you have one pole. Okay. That is why you are getting that one pole as S is equal to minus 1 by RC. So, what I am going to say is that in this transfer function actually there is only one pole. If there is only one pole, you will get the slope of minus 20 dB per decade. You will get a slope of minus 20 dB per decade. It can be proven that you will get a slope of minus 20 dB per decade. So, one pole actually means that one pole means that you will get a slope of minus 20 dB per decade. Now, how this is actually acting as a low pass filter? This is a low pass filter, I told you. Now, why this is a low pass filter? Whenever there is low frequencies, your capacitor reactance is very high. For example, if omega is equal to 0, then this part become 0. So, I will just write the magnitude response, then it is clear to you. 1 plus j omega RC. So, what is the magnitude of V out is equal to magnitude of V in divided by square root of 1 plus omega square, R square and C square. Now, you see what is happening here when omega is equal to 0. When omega equal to 0, you will get V out, which is equal to V in. Okay. Now, when omega is very high, what will happen when omega tends to infinity? What is happening here? 1 by omega, you have a term 1 by 1 plus omega square. So, 1 by infinity, it become V out becomes 0. That means that as you are having a characteristic something like this, and this having a slope of minus 20 dB per decade. And what about the cutoff frequency? That we will come to that later. Okay. So, what is happening to this cutoff frequency? Now, suppose, okay, I will just describe here itself, and okay, if omega is equal to 1 by RC, what is happening here? When omega is equal to 1 by RC, you will get V out is equal to V in divided by the magnitude of V out, I am saying, okay, magnitude of V out is equal to magnitude of V in divided by square root of 1 plus 1, right? Because when omega is equal to 1 by RC, omega square into RC square will become 1. So, this become V in by square root of 2. That means it is nothing but the critical frequency. So, this omega is equal to 1 by RC is the critical frequency. It is the critical frequency, or F is equal to 1 by 2 pi RC is nothing but the critical frequency. So, how your critical frequency is determined? Here your critical frequency is determined by using the capacitor and the resistance, or it is depending upon the time constant basically. So, this is your critical frequency. At critical frequency, you are getting V out is equal to V in by square root of 2. We have already discussed about this regarding the critical frequency. At critical frequency, the output will be input by square root of 2. That means it is having only half of the power, and all the frequencies above the for all the frequencies above critical frequency, you will be getting very small gain. Okay. So, this is a circuit, and this filter actually it contains only the passive components. So, this is a passive filter. Passive filter, and this is a low pass filter anyway. passive low pass filter because it contains only passive components. And what is the what is the slope of this curve? It is nothing but minus 20 dB per decade. But there are some other cases also, like you are using here only one capacitor, that means one energy storing element. I will say you have one RC, or you can say one pole set, or one energy storing element effectively. Okay, that's why you have one pole and you are getting a slope of minus 20 dB per decade. Suppose you need more slope, actually suppose I am saying you need something very fastly decaying like this, then it's something good filter, because I told you the ideal property of a filter is like this sharp transition. You can say this is a sharp transition, it's very sharp. Okay, it's practically difficult to obtain. Now you can see here that at Fc you have a gain, okay, and at this frequency, that means at 10 Fc you will get here as a minus. Okay, my drawing is not correct, that's why I will draw it perfectly. Now this is my okay. Now you see at 0 dB the gain was at Fc the gain was 0 dB. Now at 10 Fc the gain is minus 40 dB. So this is 0 dB and this is actually the gain is minus 40 dB. So that the slope of this curve is now minus 40 dB in 1 decade. It's decaying fastly, that means minus 40 dB per decade. Or we can say that it needs two poles. So one pole is actually giving you minus 20 dB. So one pole always give you minus 20 dB. Now if you have two poles in the circuit, you will get a slope of minus 40 dB per decade. Okay, then what is the order of the filter? For the first case, for example, the order of the filter is first order, because there is only one pole. And what is the order of this filter? The order is second order, because you have two poles. Now if you have three poles, then we will call it having a slope of minus 60 dB per decade, and the order is actually the third order. It's third order. If you have fourth order, that means you need 4 capacitor at least. Okay, fourth order filter, 4 poles, then it's become minus 80 dB per decade. So if you want something like this, a sharp transition, the slope is infinity, you need actually infinite number of capacitor. That means that practically it is not possible. Okay, it's practically not realizable, it's not possible, it's difficult. So 4 poles will give you the order 4. Okay, it's a fourth order filter. So this is the characteristics of the filter. Now I will draw one more anyway here to distinguish correctly. So I will use this color. Okay, so if you have you need actually, here is 60, so I need to join through this way. So this is having more slope anyway. The slope is minus 60 dB per decade. Okay, so it is a 3-pole filter. So you see here, when I increase the order, actually the curve is moving towards the ideal response basically. So you see the curve is now moving like this, it is moving towards the ideal response. So the first order will give you minus 20 dB per decade. It's not so bad, it's not so good anyway. Minus 40 is okay, and then minus 60 if you are using a fourth order you will get minus 80 dB per decade. Okay, I have no space here, that's why I am not showing. So this is about the low pass filter, and we have already seen a low pass filter, and this filter is a passive filter. But in this course we are talking about op-amp, so we will talk about the filter with an amplifier also. That means we will be having an amplifier circuit. That means amplifier is an active device. So we will use the filters with the amplifier also. So we will talk about the active filters in this course. What is active filters? It contains the RC network, basically RC network that we have seen, and it also contains the amplifiers, okay, or the active elements amplifiers. Okay, so we will talk about this later. Okay, we will discuss later. So before that we will see what is a high pass filter. Now we will see what is high pass filter. The same thing, high pass filter. You just need to, for a passive high pass filter, what you have to do, you have to just replace the resistance with the capacitor and the capacitor with the resistor, so that you will take the output from here, V out, and this is your V in. So what is your V out? So this is R, this is 1 by SC, I told you, or 1 by omega RC, okay, not omega RC, 1 by omega C. So V out is equal to V in divided by 1 by SC plus R multiplied with R. So you will get here as V in into R divided by 1 plus R SC divided by SC. Now this become V in into SRC divided by 1 plus SRC. Okay, that's it. Now if you want to find the transfer function of this filter, it's V out by V in is equal to SRC divided by 1 plus SRC. You can see here that how many poles are there. This is the pole. How to calculate? 1 plus SRC is equal to 0. So S is equal to minus 1 by RC. So the pole is at the same location anyway. So what is the difference here? You have a 0 here. So this is nothing but the pole. Now we will talk about the 0. That means SRC is equal to 0. That means that S is equal to 0. So there is a 0 at origin. There is a 0 at origin and there is a pole. So that's why you have the characteristics of the high pass filter that I will show you. So there is you should know that this is a first order filter. Why I am talking about first order? Here you see this is a first order filter because there is only one pole. So this is a first order. So one pole. So this is a first order. So what is the slope you can expect? You can expect minus 20, right? Minus 20. But here you see it's not minus 20, it is plus 20 because it is a high pass filter. We will see the response now. So this is the frequency. I will talk about the response like this, and this is going, and this is your 0 dB, and this is your FC. Okay, your FC is somewhere here. So it is allowing all the frequencies above FC. Why the characteristics is like this? It is allow all frequency above FC. And what about the frequencies below FC? It rejects frequencies below FC. That's the characteristics like this. That's why the characteristics is like this. Now we will see the response now. Okay, and what is that response? V out is equal to, we will see just equation. Sorry, this is the gain anyway, I forgot to write it. So gain. So the response is equal to V in into SRC by 1 plus SRC. So V in into SRC divided by 1 plus SRC. I will put S is equal to j omega, that's it. Okay, that's very easy in the terms of S is equal to j omega. You know how to find the frequency response, you have studied in the automatic control, I think. So it is j omega RC divided by 1 plus j omega RC. So I will find the magnitude of V out as, okay, this is nothing but V in into, so magnitude of V in into omega RC divided by square root of 1 plus omega square R square C square. I am just taking the magnitude of the numerator and the denominator. Now what is happening here? Okay, now we will see when, so what is V out? Magnitude of V out is equal to magnitude of V in into omega RC divided by square root of 1 plus omega square into R square into C square. Now we will see what is the omega when omega is equal to 0. Okay, that's it. Now we will see at omega, and this is the gain. At omega equal to 0, the output is equal to 0, because you see there is a term here omega. So 0 into something, its output is equal to 0. Or we can say the gain, okay, V out. We will say V out. So V out is equal to 0. When omega is equal to 1 by RC, what will happen? V out is equal to V in divided by square root of 2, because you see omega RC become omega into RC. That means it is omega is equal to 1 by RC, 1 by RC into RC. This become at omega equal to 1 by RC. What will happen? This become 1, and this square root of 1 plus omega square R square C square become square root of 1 plus 1 by RC the whole square into R square C square. Again this become square root of 1 plus 1. This is nothing but square root of 2. That's why you are getting the square root of 2. Now when omega is equal to infinity, then what will happen? At omega tends to, as omega tends to infinity, then V in, that is your V out, is equal to omega RC divided by this 1 plus omega square R square C square become, when omega tends to infinity, it is approximately equal to omega RC, because why? This become square root of 1 plus omega square R square C square. This is approximately equal to V in into omega RC divided by square root of omega square R square C square. This is equal to V in into omega RC divided by omega RC. That means if you take the limit, you will get it as V in. So V out is equal to V in. Okay, so you are getting a characteristics. At low frequency you have no output, and as the frequency increases, and if the frequency is above the cutoff, it is allowing all the frequencies. That means that your characteristic curve is something like this. It is something like this, and it is allowing the frequencies. So this is Fc, then this frequency is 0.1 Fc. Why I am saying I am taking like this? Because it is 1 by 10th. For example, this is 10 times. 10 times. This frequency is 10 times this. And this is nothing but 0.01 Fc. Okay. And this is 0.001 Fc. So all these are 10 times. Okay. And if this is a one pole filter, as we considered here, it's a one pole filter, high pass filter, then what is it? If it is a one pole high pass filter, then the slope of this line, as discussed, I told you it is minus 20, but here the slope, you see, it is increasing the positive direction. So in the previous it was decreasing, like this, but now it is increasing. So the slope is plus 20 dB per decade. That means that suppose you have a gain here at 0 dB, at this point you will get minus 20 dB, and this point you will get as minus 40 dB, and at this point you will get minus 60 dB. That means initially it was minus 20. Actually, for example, if you take this point, it is minus 20 and it is increased to 0 dB, and here you see here it is minus 40 and it has become minus 20 after 1 decade. So this is the decade response. Okay, all these are, this is the decade frequency. So now see here that the gain is increasing. So what is happening here? It is a one pole filter. That's why one pole, it is having one pole. Okay, that's why it is having one pole, and there is a 0. That's why it is increasing. Okay, so basically it is increasing because of that 0. Okay, so the slope is plus or minus 20. It is according to the number of poles and zeros. And now you see so there is a 0 and okay. So the order, I can say that the order is equal to 1, order equal to 1. Now if the order is 2, you will be getting a response like this. This is order 2. That means plus 40 dB per decade. So this is what happening in the filters. So this is the filter response. So this is the high pass filter. Okay, high pass filter. And I told you that the filter that we have seen, it is a passive filter. This is a passive filter. This is a passive filter. In active filters, we will use the amplifier also. That we will come to that later anyway. Now we will see what is a band pass filter. Band pass filter. What is band pass filter? You see, it is having a characteristics like this. Band pass filter means it will allow the frequencies in a particular range. For example, it is having some particular range of frequencies. So these are the range of frequencies. This is some FC1 and this is FC2. Okay, so it will allow the frequencies between FC1 and FC2, and it will not allow any other frequencies between in another range. Okay, so how you can make it? You can view this band pass filter, and also the same thing is like a minus 20 dB per decade, and this can be plus 20 dB per decade. So this is maybe the first order, and this is also first order response. So what is this? You can actually view this in another way. You can view that the first part, okay, this part is actually, I am drawing like this. You have a high pass filter, and after that you see you have the second part. This is the second part. The second part actually coming from a low pass filter. My drawing is not good, that's why. Is a see, low pass filter. So this is a low pass filter. So what is you are getting? You are getting a response of both low pass and high pass. So if you know how to design a low pass filter with some critical frequency, this is FC2, and you have an high pass filter with a critical frequency FC1, if you know both, then you can find you can get the band pass filter. So if you have a first order, for example, if you have a high pass filter first, then you have a low pass filter, you can combine, or you can use high pass filter, low pass filter also, it's no issue. So you have an high pass filter with the cutoff frequency FC1 and this low pass filter with the cutoff frequency FC2, you will get the band pass filter. So this is showing the band pass filter. So the band pass filter is a combination of high pass and low pass. So if you know how to make a low pass filter and high pass filter, you can basically make the band pass filter. So how it will be the passive filter? The passive filter will be looking like this. You know what is this? This is a high pass filter. Then you take this output and connect to a low pass filter. So this is low pass filter now, and you take the output here, this is V out, and you give here input V in. So this is a passive band pass filter. So this, let's say this is C1, this is R1, and this is R2 and C2. So what is your FC1? FC1 is equal to 1 by 2 pi R1 C1, okay, and what is FC2? It is 1 by 2 pi R2 and C2. So you can make the low pass filter and high pass filter, and if you choose this FC1, and you see here that your FC1 is less than FC2. If it is in another way, it is become another filter. So here you have to note that your FC1 for the high pass filter is less than FC2 for the low pass filter. Then it become a band pass filter. Okay, this is a passive filter. We will talk about the active filter later. Now you have one more filter. It is the band reject filter. And before that, I forgot to write about the center frequency. Okay, the center frequency is F0, and the F0 is given by the geometric mean of two frequencies, FC1 and FC2, square root of FC1 into FC2. It is the geometric mean. It is the average, geometric average, geometric mean. Why I am taking geometric mean? For example, your high pass filter is a second order, and your low pass filter, if it is a first order, then the response will be something like, if this is first order and this is second order, then it will be, the response will be like this, because it's become 40 dB per decade and this become minus 20 dB per decade. Sorry, this become 20 dB per decade slow, and this become minus 40 dB per decade. So the mean is the center frequency is somewhere here. So it will be depending upon all these characteristics, FC, okay, all these characteristics. That's why we are using the geometric mean. Anyway, we will talk about the band reject filter. So band reject filter is basically, you will get a characteristics like this, and you will get something. This is the characteristics, so like this. So this is FC1 and this is FC2. So you can you have the response like this. You can basically see, you can see this is a low pass filter and this is a high pass filter, but you see your FC1 is less than FC2. FC1 is for the low pass filter and FC2 for the high pass filter. That is the difference anyway. And you can also make it by in the same way, but there are some other kind of designs also that we will see later. So this is a band reject filter, okay, band reject filter, and this is also having the center frequency F0. And how to find F0? It is the square root of FC1 into FC2. So this is how you can find the response of a band reject filter. So we have seen all the characteristics, sorry, all the type of filters. Now we will talk about the filter characteristics. Filter response characteristics. We have only seen the response characteristics in terms of slope. That means we have seen that minus 20 dB per decade, or plus 20 or plus 40 or minus 40, like this. But there are some other response characteristics. According to that, it can be classified. You know, suppose if I take a low pass filter, suppose I consider a low pass filter, suppose this is the gain of the low pass filter, okay. Now you know that the typical characteristics is like this. Okay, this characteristics we will call it as the Butterworth response. Butterworth characteristics or response. But there are some other characteristics the filter may exhibit. Some other characteristics, you can see that in some filter your pass band is having some oscillations or ripples like this. It's not oscillation, it is ripples. The gain is changing. Okay, and this filter is having a good transition, this fast transition. You can see the slope is actually very high, actually fast transition, and this type of response is known as Chebyshev filter. Chebyshev, it's the name of the Russian scientist. Okay, Chebyshev response. And we have another characteristics which is having a more transition band. So that is known as the Bezel characteristics. So I will draw it. Okay, I will draw it. Okay, my picture actually is not so good. I will just redraw again. Okay, it's like this. Okay, like this. Now I have one more characteristics, that is known as the Bezel characteristics. The Bezel characteristics is something like this. It will start like this, but it is having a transition. It's very slow. This is the Bezel characteristics. Bezel response. So it is nothing but the frequency response of the filters. The frequency response of the filters seems to be like this. It's following this particular pattern based on your design and based on your how to place the capacitor, all these things. So I will describe each one of them now. So Butterworth characteristics. It's very flat. It's very flat. You can see it's a flat characteristics. It's very flat here. Okay, it's very flat characteristics, not fat. It's flat characteristics. And one pole actually means that you have a slope of minus 20 dB per decade. That is the meaning of one pole in Butterworth response. And the Chebyshev response also, it's not flat. Okay, it is not flat. And but you see here the roll off, actually this Butterworth response is having a roll off rate of minus 20 dB per decade for one pole. Okay, this per pole we can say. And this is also having minus 20 dB per decade per pole. That means for one pole it is giving you minus 20 dB per decade. So that's what in Chebyshev, but it is like ripples are there, the pass band ripples in pass band. Now another response is the Bezel response. It's flat response, but it is not having the slope of minus 20, but the slope is not minus 20 dB per decade. It's not minus 20 dB per decade. It's flat response, but so slow roll off. We can say roll off for this phenomenon. That means the gain is decreasing. This is nothing but the roll off. Okay, all these characters we will call this slope actually as the roll off. This roll off. Okay, or we can say this is roll off. Okay, this roll off rate is high in in Chebyshev, and in Chebyshev I have made a mistake here. In Chebyshev filter, the roll off is greater than, not flat, and the roll off is greater than roll off is greater than minus 20 dB per decade. It is above. So this is Butterworth, then Chebyshev, Butterworth, then Chebyshev, okay, Chebyshev actually, I think Chebyshev, okay, Chebyshev, and is Bezel. So here Butterworth is minus 20 dB per decade per pole. The roll off is equal to. So I am talking about roll off. How fast it is decaying, that's it. This is the decay rate, okay, that's the roll off. Now Chebyshev means it's greater than minus 20 dB per decade per pole, or we can say it's greater than it is, this is less than minus 20 dB per decade per pole. That's it. So these are all the characteristics. Now we will see, we have now seen the passive filters. Basically we have seen the passive filters. Passive filters will consist of R, C and L elements anyway. You can also make the filters using L inductor. And now in active filters, it contains R, C, L, and it contains a special thing, it's amplifier. That means it is made using transistors. So whenever you are using the transistors, you have actually an active filter. So we will talk about the active filters now. So active filter, active filter. So you have an input V in, and this is the frequency selective circuit. That means I told you it can be R, C or L elements, okay, R, C or L elements. And you have an amplifier using op amp, and this amplifier is having a gain. The circuit analysis is little bit complex, so I will not be going into much detail about the circuit analysis. If you want to do the circuit analysis, convert everything into S domain and you can perform the circuit analysis. Now I will just give you, so this is V out and this is the negative feedback, okay, and the output is given here directly, and one part of the output of this frequency selective is given here directly, and there is a feedback in the to the RC network, there is a feedback to the RC network also. So this is the active filter structure. According to the design of frequency selective network, you can make low pass filter, high pass filter, band pass filter, etc., and band reject filter. All this can be made by adjusting your RC network or RLC network. Okay, sometimes you will be using, anyway we will be using already RC network here in this course. So by adjusting the RC network, you can make the active filter, which may be low pass filter, high pass filter or band pass filter. And one more thing, you can see there are two resistors. You have to remember this formula. The damping factor dF is given as 2 minus R1 by R2. And what do you mean by this damping factor? Suppose you have a second order response, you might have studied in the automatic control about the second order about second order transfer function. What is that second order transfer function? It is given as omega n square divided by s square plus 2 into theta into omega n into s plus omega n square divided by s square plus 2 into theta into omega n into s plus omega n square, and this number is the damping ratio, and it is a ratio between it can be 0, maybe sometimes some less than 1 or greater than 1, and according to that your time response will be changing like this. If you have an oscillatory behavior, you can have something like this, you can have something like this. So all these are all the time response characteristics that you have studied, and this is having the damping ratio less than 1, this is equal to 1, theta equal to 1, and theta less than 1, this is theta greater than 1, and you will get something like this. This is always oscillatory when theta equal to 0. That means their roots become complex. So this is the second order transfer function. So whenever we talk about the second order filters, so damping ratio, when we talk about the second order filters, it is nothing but your damping ratio theta actually. So how this is determined? It is determined after the circuit analysis. When you do the circuit analysis, it can be found that the damping ratio is determined by 2 minus R1 by R2. So I am not going for the complete circuit analysis. Those who are interested, they can do by themselves. It's a very complex circuit analysis. A lot of steps are required anyway. So now we will see a first order filter, which is a low pass filter. I told you about the low pass filter. So we will now talk about the active low pass filters. So we will see a first order filter. Okay, first order filter. So what is that? You have an amplifier now. So what I have told you is that for this this damping factor is only for the second order filter. It is not for the first order filter. So don't confuse with it. Now you see, this is plus minus. This is V out, just an amplifier with a negative feedback, and this is R2. That's it. So what is the closed loop gain? If you give here input, some input, what is the closed loop gain? The closed loop gain of the non-inverting amplifier, it is a non-inverting amplifier because the input is given to the non-inverting terminal. It becomes 1 plus RF by RI. What is RF here? This guy is RF here because R1 is your RF. So 1 plus R1 by R2. This is a closed loop gain. But we are designing a filter. It's a low pass filter. So what we will do, this input is not as direct input. We will use a RC network. I told you about an RC network with like this. This is your V in, and you will take this here. So this is your RC network. This is a passive filter. This part is passive filter. Now total it become an active filter. This part is a passive filter, and this total become an active filter. Okay. So you see here that this is the active low pass filter. And what is the cutoff frequency? I have already told you the cutoff frequency for this filter is 1 by 2 pi RC, or I can say 1 by or I can say that my omega C, that means angular frequency, 1 by RC. Okay. So anyway, this is not required. This is your cutoff frequency. So it's very easy thing. So you just need to select some value for R and C. Then you can design a filter. Okay. I hope this is clear to you. So we will see an example now. Design a first order active low pass filter with cutoff frequency 100 hertz. Assume R is equal to 1 kilohertz. Okay. So, if I give a design problem, then what you have to do, you know that what is FC, it is given as 100 hertz. So, and R is also given as 1 kilo, not 1 kilohertz, 1 kilo ohm. R is given as 1 kilo ohm, 1 kilo ohm. So, FC is equal to 1 by 2 pi into RC. So, how much it will come? What is that C? C is equal to 1 by 2 pi R into FC, right? This become 1 by 2 pi multiplied with, what is R? R is equal to 1 kilo, that means 1000, multiplied with, what is FC? It is 100. So, this is your C. You can calculate this. Now, you have to draw the circuit diagram. You have the V in. Now, I will draw with a different color. Your V in, and I am talking about a low pass filter. So, in a low pass filter, first I will be using a capacitor, and R is equal to 1 kilo ohm. And what is your C? I told you about C. The C is equal to 1 by 2 pi. I don't know what is this answer. 1000 into 100. This is your C. Now, you have to draw the amplifier, plus minus. You have a feedback which is R1 and R2. That's it. Now, you connect like this here. Okay. This is your V out. So, this is a active low pass filter with FC is equal to 100 hertz. According to the different value of FC, you can find the different values for the capacitor. Sometimes I will not give you R and C. In such a case, you just assume R equal to 1 kilo ohm or 10 kilo ohm, whatever you want. Okay, no issue. Now, what is the closed loop gain? You can fix the, okay, I will just add one more sentence in the question. Assume the mid-range gain, because I told you this is the response of this. So, this is actually the mid-range we have already seen. Assume the mid-range gain is equal to 100. So, if the mid-range gain is equal to 100, then the closed loop gain, it is nothing but 100, which is equal to 1 plus R1 by R2. Okay. Then 99 is equal to R1 by R2. Suppose R1 is equal to 1 kilo ohm, then R2 is equal to 99 kilo ohm. So, you assume here this is 1 kilo ohm, then this is 99 kilo ohm, so that you will get the gain of 100. Okay. And you can assume in any way. Suppose you can, if somebody is assuming 10 kilo ohm for R1, then he can get another answer, no issue. Otherwise, I will give in the question. Okay. So, here I will give, assume R1 equal to 1 kilo ohm. Okay. That's it. That's why I am assuming here. So, this is the problem. Now, we will see a second order. So, this is a first order filter. So, this is a first order filter. This order is 1. That means you have only one pole. Now, we will see the second order filter, second order low pass filter, which is active filter. We will see a second order filter. In second order filter, it is coming under a, we will call this second order filter with another name also. It is the Sallen key low pass filter. This is an active filter. This is the name of this filter anyway. So, I told you again we have plus minus, this is R1, this is R2, we have a negative feedback. That's it. Now, we have the input. Since we are talking about second order means two poles. So, 2C or 2 RC networks you can see. So, you see here there is one RC network here, this is RA, and you will get another one which is RB here. Then you have a capacitor here which is CB here, and you have another capacitor, this is CA here, which is connected to the output, and this part is connected to the input. So you have RA, RB and CA and CB as connected like this. And if you want to find the response of this, you have to apply the Kirchhoff laws and you need to find the output. But I am not going to solve this completely. It can be found that the response FC, the critical frequency, is depending upon RA, RB and CA, CB. It is given as 1 by 2 pi square root of RA multiplied with RB and CA multiplied with CB. If CA equal to, if RA equal to, so this is your critical frequency for the low pass filter, and the response will be like this, as I told you. This is your FC and this is the gain. And what is the slope of this? The slope is minus 40 dB per decade. Why? Because this is a second order filter. This is 2 pole and this is a second order filter. You can see one pole here. That means RBCB will form one. RBCB is one pole here, and RACA is another pole here, one pole. So there are 2 poles. That means it is a second order filter, second order. Okay, and if RA equal to RB is equal to R and CA equal to CB equal to C, then you will get your FC as 1 by, if you substitute in this equation, you will get 1 by 2 pi RC, if all these resistance are same. Okay, so this is, and one more thing about this filter. So I told you about FC as 1 by 2 pi into RACA, sorry, RARB into CACB, or if RA equal to RB equal to R and CA equal to CB equal to C, then FC is equal to 1 by 2 pi RC. And also we have to talk about this damping factor. Okay, the damping factor will give you its response. So damping factor is given as 2 minus R1 by R2. So according to the damping factor, you can design this filter, and this will be given from the table. So we need a table for designing this. So I will give you the table anyway. Okay, this will be given. Now this is the second order filter. So if you want a third order filter, another example, if you need a third order filter, then you can use a second order filter first, then you can cascade. This process is known as cascading. That means then you can use a first order filter. That's it. Okay, so this is V in and this is your V out. So we are just now talking about third order low pass filter. So we have the filter like this. First you will use plus minus, and you know this is R1 and this is R2, and I connect like this. Now this is this is RA and this is CA and this is RB and this is CB. Don't confuse. That's it. Now this is, so what is that? This is a second order filter. Second order. Now I take this output and I connect to the first order filter. This is RA. Okay, this is RA1. Okay, and CA1. So this is RA2 and another CA2. Okay, now you have positive, negative. You have another 2 resistance. Let's say R3 and R4. This is your output, V out. So what is that? This is a first order filter. So what is the slope of this? If you take the response of this guy, you will get something like this. What is that slope? It is minus 60 dB per decade, because one pole will give you minus 20. There are 3 poles, so 3 into, because there are 3 poles, so 3 poles means what? 3 multiplied with minus 20. That means this is nothing but this. How you are getting it is 3 into minus 20, which is minus 60. If that is 4 pole, then you will get 4 into minus 20. Now we will see another example. If you need a fourth order filter, then you just couple 2 Salon-Key filters. That means fourth order low pass filter. Then what is it? You have R, so RA and CA. Draw like this, then it will not be confusing. This is RB and CB. That's it. Now you have plus minus R1, R2, connect like this. This is V out 1. Take this output, again you connect. So okay, this is RA1, CA1, RB1, CB1. So this is nothing but a second order filter. So this is RA2, CA2, then RB2, CB2, connect this to the ground, plus minus, this is R3, R4, V out, and I connect this guy here. So this is another second order. So the total, it is fourth order. So there are 4 poles. So your characteristic curve will be like this. It will be like very sharp. This become minus 80 dB per decade. Okay, because 4 poles means what? 4 into minus 20. This means minus 80. So minus 80 dB per decade. So this is a critical frequency. So FC. So if you use all the filters are having same R and C, then the design become very easy. Okay. So that is the 4 pole filter. Now I will give you the table. You see here that the damping factors are given. For example, for the first order filter nothing is given, but for the second order filter, you have the damping factor, it is 1.414. So for the second order filter you have the damping factor 1.414. And for the third order filter, third order means you have to use a second order, then you have to use a first order. So for the third order filter, you can see the second order filter is having a damping factor of 1, and the second stage is having a damping factor again 1. Okay, then the fourth order filter, you can see you have to use 2 second order filters. Okay, so for the first second order filter, that's it. Fourth order, you just see this, it is 1.848 is the damping factor, and for the second part you have to use a damping factor 0.765. so you can see this, okay, damping factor. And you know that the damping factor is equal to 2 minus R1 by R2. So basically you have to find what is the value of R1 and R2. That's why you are using this damping factor. So damping factor, actually this to find R1 and R2. So instead of using the damping factor, you can directly use the ratio of R1 and R2 also. So that is also given here. So if a table is given, you can easily calculate all these things. So we will see a problem, then it will be very clear to you. So problem, determine the critical frequency of Salon-Key low pass filter given below, and set the value of R1 for an approximate Butterworth response. Okay, Butterworth response. So all these filters now we have discussed all are nothing but the Butterworth response filters. So whatever design actually that we have considered, this by using this table is for the Butterworth response. So we will be discussing only the Butterworth response in this course. Okay, other response need another kind of features, actually they another table or another required data, another data is required for that, but we will now talk only about the Butterworth filters. So it has been given that there is a, okay, I will, this is your RA, then that is your CA, okay, then there is your RB and there is your CB, then it's grounded, sorry, then you have something plus minus, this is R1, this is R2, then this is connected here, okay, this is your V out. It has been given that this is V in, all these are given, this is 1 kilo ohm, this is also 1 kilo ohm, this is given as 0.022 microfarad, this is also given as 0.022 microfarad, okay, and R1 is not given, but R2 is 1 kilo ohm. Now you have to find what is the critical frequency and you have to find what is the value of R1. So you have to find what is R1 and what is FC. You see here that all the values of resistors are A and RB. Here you see RA equal to RB equal to 1 kilo ohm, and you can see CA equal to CB is equal to 0.022 microfarad. Both are same. So the critical frequency is very easy to find, 1 by 2 pi, just take, you can take, this is R and this is C, 1 by 2 pi RC, which is nothing but 1 by 2 pi into R is 1 kilo ohm and C is 0.022 microfarad, and you will get this answer as, let me check the calculation, you will get this answer as 7.23 kilohertz. That's the cutoff frequency. So if you draw the response, you will be getting like this, and this is nothing but FC is equal to 7.23 kilohertz. Okay, and this is this is the gain, and this is a second order filter, because this is a second order filter, it's a second order. So the frequency response will be having a slope of minus 20 dB per decade. Okay, this is having a slope of minus 20 dB per decade. Now we need to find what is the value of R1, but you know that what is the damping factor for a second order filter. We have to see the damping factor of a second order filter. You see, for a second order filter, just take this response. For a second order filter, the damping factor is 1.414, or R1 by R2 is 0.586. So the damping factor is 1.414, or R1 by R2 is equal to 0.586. Okay, this damping factor is 2 minus R1 by R2, which is equal to 1.414, or you can say that R1 is equal to 0.586. If you solve this equation, you will get the same thing. So you can either use the damping factor or R1 by R2. So what is R1 by R2, which is equal to 2 minus 1.414 is equal to 0.586. So what is R1? R1 is equal to 0.586 multiplied with R2, which is equal to, what is R2? R2 is 1 kilo, 0.586 into R2 1 kilo, 1000 ohm. So this become 586 ohm. So you can find it. So this is the problem. Now we will see another problem, which is a design problem, okay, which is a design problem. That means you have to design a filter for you have to design a filter for a particular frequency. So question number 2, design a fourth order, or you can say 4-pole filter. That means it is having minus 80 dB per decade as the roll off rate, okay. 4-pole filter with Butterworth response, and it is a low pass filter, okay, low pass filter, 4th order low pass filter. So with FC, that means the critical frequency 2680 hertz. Assume, you can use this assumption, assume all resistors in RC networks are equal. Also select the values for feedback. That means you have to select R1 and R2 in the feedback, that is for feedback resistors to get Butterworth response. So when you get a question like this, it is a design problem. For a design problem, what you have to do, you have to draw the circuit first, then find values. So this is these are the 2 steps. Find values for all components, okay. So I will first draw the circuit diagram. You know that it is a 4th order filter. So 4th order filter with a roll off rate is minus 80 dB per decade, because it's a 4th order. How they are getting it is 4 into minus 20, that is minus 80 dB per decade. So you can use 2 second order filters. Second order we know how to design, it's very easy. So second order filters, so that you will get 4th order. So this is your V in and you will get the V out here. So we will just use our circuits. You know that it is all the resistors are equal also, okay, all the resistors are equal. That means that you have R here and R here, and you have another R here, and this is C here. So this is C, R, C, okay, and this is this is plus, this is minus, and you have something like R1, and this is R2, and you connect like this. So this is giving you second order response. Now next, again you have R, you have C, you have R, and you have C, and this is plus, this is minus, and this is R3, and this is R4. Now you can connect like this. So this is again a second order, so that you get the 4th order filter. Now you see all the resistors are equal, so it's very easy to find the critical frequency. It is 1 by 2 pi into RC, okay, RC, and it has been given that you can select any value for R and C, R or C, according to a critical frequency, and the critical frequency is given as FC is given as 2680 hertz. So I am assuming some standard value for RC. So I assume that what is that? Let me check the assumption. Yeah, I assume that the resistor is, all resistors are, all R takes the value 1.8 kilo ohm. Okay, then I can find my C is equal to 1 by 2 pi R into FC, that is nothing but 1 by 2 pi 1.8 kilo ohm. You can use 1 kilo ohm also, okay, if nothing is given. If in the problem, if I have given a value, please use it. Then into 2680 hertz. So you will get this as 0.033 microfarad. So all this you will get, this is 1.8 kilo, 1.8 kilo, this is 1.8 kilo, this is 1.8 kilo ohm, and this becomes 0.033 microfarad. This is 0.033 microfarad. This becomes 0.033 microfarad and 0.033 microfarad. Everything is same. Now we have to find our R1, for example, R1, R2, R3 and R4. So I am assuming with another assumption, I am just considering another assumption. Assume that your R2 is equal to R4 is equal to 1.8, because I am using the same resistance, but the damping ratio, because we see here this is a second order and another second order. So we will see the table now. We will see the table now. Okay, we will see. I will import the table there itself, no issues. So we see the table now. So when I use the table for the fourth order filter, you see I have the first stage, this one, and the second stage, this one. Okay, I can use this part, or I can use this. I can use this R1 and R2. So you see here, for the first part, R1 by R2 is equal to 0.152, or I can use the damping factor and then solve and find the R1 and R2. So what is R1? R1 is equal to 0.152 into R2, which is equal to 0.152 multiplied with 1.8 kilo ohm, which is equal to 274 ohms. So this is nothing but 1.8 kilo ohm, and this become 274 ohms. Now we need the second stage. Okay, this is the first stage. The second stage, you see it is 1.235. So R3 by R4 is equal to 1.235. Therefore R3 is equal to, R4 is 1.8 kilo ohm multiplied with 1.235. You will get this is 2.22 kilo ohms. So just put it here. This is 1.8 kilo ohm, and this become 2.22 kilo ohm. Okay, you got it. So you got all the values now. So this is a fourth order filter, and the roll off rate of this filter is you will get the response like this. You will get the response like this with a minus 80 dB per decade. So this is the filter design. So I hope that you can design the third order filter also in the same way. Okay, I hope you understood this, the design of the Salon key or the Butterworth design of any order. Okay, so for the exam I may ask for first order, sometimes I ask for second order or third order. Third order also you can use, and the third order will be having a roll off rate of minus 60 dB per decade. Now we will see how to design the high pass filter. High pass filter. But you know that for a passive high pass filter, we have, this is the RC network. This is C and this is R, and this is your V out and this is your V in. This is the case of passive. So for the first order filter, we will use the same circuit. This is plus, this is minus, same circuit in the low pass filter. This is R1, R2, and this is your V out. But here you see I will use this network. That means that I will use the capacitor here and resistor here. So this is R and C. Now this is V in, and I connect this one here. So this is a first order high pass. What is the roll off rate? The roll off rate you see here, it is something like this. It is 20 dB per decade, the roll off rate. This is a high pass filter. You can use the same table anyway for designing the high pass filter, Butterworth response. Now you see here that we are having the first order high pass filter like this. Okay, so this is the first order filter. Now cell and key filter, same way, cell and key high pass filter of second order. The same way you can design the filter. I told you in a low pass filter, actually you have the resistor here, but here you have the capacitor. Okay, capacitor, then you draw the resistor. So this is your CA and this is your RA. Just you swap the position of the capacitor and the resistor, then you will get the high pass filter. Then this is CB and this is RB. Okay, now you connect here, this is plus, this is minus, same thing, no change, just you need to swap the position of the capacitor and the resistor, and you connect this here. Okay, so this is your V in and this is your V out. And what is your critical frequency? Critical frequency is 1 by 2 pi square root of RA, RB, CA and CB. Okay, if all are equal, if RA equal to RB equal to R and CA equal to CB equal to C, then FC become 1 by 2 pi R into C. And what is the response? You can get the response of this filter as the high pass filter, and this is your critical frequency. And what is the roll off rate? It is 40 dB per decade, second order. Okay, in the previous case it is 20 dB per decade. Now it is 40 dB per decade because there are two poles. So you will get 2 into 20. This is nothing but 40 dB per decade. That's it. So this is how you can design. And to find the values of R1 and R2, you can use the damping factor. Damping factor, same formula, 2 minus R1 by R2, and use the table. Okay, so this is the second order filter. Now if you want a fourth order high pass filter, so use two second orders, second order high pass filter, then connect again the second order high pass filter. So in this case actually you have 4 poles, so 4 into 20 is nothing but 80 dB per decade. So if you see the response of this, you will get something very sharp response. So this become 80 dB per decade. Now for the third order, it's very easy. You can use the second order and the first order, and you can use the same table. Okay, this is the third order. So I'm not going to discuss again all these things because it is having the same procedure as that of the low pass filter design. Now we will see a problem with the high pass filter design. So question number 3, design a high pass filter with roll off rate of 40 dB per decade. That means it is 40 dB. That means what? It is a second order filter because 40 is nothing but 2 times 20. So 2, it is a second order filter with a critical frequency of 10 kilohertz. If all the resistors in RC circuit are equal, assume that, okay, not if, assume that all the resistors are equal. Okay, also select the values of feedback resistors to get Butterworth response. Okay, if you change this, if you are not selecting the feedback resistors according to the table that I have given, then everything will be different. Actually, it will give you some other response like Chebyshev or something. It can be, we cannot predict it. So the Butterworth response you will be getting only if you are using that table. So all these things are pre-calculated and they have made the table for this. Okay, now I will first draw the circuit diagram, because you have to draw the circuit diagram. Draw circuit diagram. Circuit diagram. So what is that circuit diagram? I will have a capacitor first, then I have a resistor here, then I have a capacitor again, then I have a resistor here. Okay, this is connected here, this is plus and this is minus, and this is your R1 and this is your R2, and this is connected here, this is C, this is C. It is given that all the resistors are having the same values, so R. Okay, now we will find what is our critical frequency. Fc is equal to 1 by 2 pi R into C. So what is that? Assume that all the resistors in the RC network are equal. Okay, so I assume here with some arbitrary assumption, I assume that my R is equal to 3.3 kilo ohm. Okay, you can select 1 kilo ohm also, there is no issue. So if I give you the value equal, okay, I will give the value and is R equal to 3.3 kilo ohm. Okay, then you can avoid the confusion. So what is that C? Then C is equal to 1 by 2 pi into 3.3 kilo ohm into Fc. What is our Fc? Fc is 10 kilo. Okay, you can just find this. So you will get it as 0.0048 microfarad. So you will get it as, so this is 3.3 kilo ohm, this is 3.3 kilo ohm, and this is 0.0048 microfarad, and this is also 0.0048 microfarad. So this is your V in and this is your V out. So you got all the values, but you have to find the R1 and R2. So for finding the R1 and R2, we have the table from the previous problem. You will use the same table. So it's a second order response. So for the second order response, you see the table is giving you R1 by R2 as 0.586. So from the table, R1 by R2 is equal to 0.586. So I will assume my R2, I will assume my, okay, you can assume R1 or R2, whatever. I will assume my R1 is equal to 3.3 kilo ohm. So my R2 is equal to R1 by 0.586, which is equal to 3.3 kilo ohm divided by 0.586. You will get it as 5.63 kilo ohm. You can use your R1 as you can use your R1 as R2 as 3.3 also. There is no issue. Then R1 become 0.586 into, okay, into R2. So any assumption is okay. So no need to worry about this assumption. Okay, now I will give you a homework problem. So anyway, before that I will give you the response. This is the response. Fc is equal to 10 kilohertz, and this is a second order filter, so it is 40 dB per decade. Okay, this is the slope of this 40 dB per decade. Now if you want to design, a third order, then use third order high pass filter, then second and first. Okay, and use the table. Okay, use the table. And what is the slope of this? Basically it will be like this, then this become 60 dB per decade. It is the slope. Okay, third order. The third order means 60 dB per decade for the high pass filter. For the low pass filter third order it is minus 60. For the high pass it is plus 60. For the fourth order you will use two high pass filters. So I will give a homework problem for your practice. Design a high pass filter with roll off rate 80 dB per decade. You see the roll off rate is 80 dB per decade. That means that it is a fourth order filter because 80 is equal to 4 times 20. So with a critical frequency of 100 kilohertz, okay, 100 kilohertz. Assume all resistors in RC networks are equal to R 1 kilo ohm. Also select the feedback resistors to get a Butterworth response. Okay, Butterworth response. Assume feedback resistors R2 is equal to R4 is equal to 1 kilo ohm again. Okay, then you have to find, so what you have to find your C, you have to find your R3 and you have R1 and R3. Then draw the circuit, then draw the response also. So the response will be like this, 80 dB per decade, and critical frequency FC is equal to 100 kilohertz. That's it. So draw the circuit. So this is a problem that you can use it as an homework. Okay, you don't need to submit this, but this is for your practice. Okay, so there are two more filters. One is the band pass filters and another one is the band reject filter. So band pass filter we will see in the next class, because band pass filter is nothing but you need one low pass filter and a high pass filter. That's it. It's very easy. So we will see the design in the next class. Okay, thank you.